Let's go over this review here, make sure we're all on the same page for the test tomorrow. So the first section was just properties of exponents. Okay, we talked about three properties, and they're all represented here. The first property, and number one, was the product property. If we are multiplying terms that have the same base, then I can add the exponents together. So there's no other coefficient here, so 4 times, this would really be a 1 we could think about, so 4 times 1 would be 4. Then if I get u to the 4th times u to the 2nd, we add those exponents, so we would get u to the 6th, then same thing, b to the 3rd times b to the 4th would be b to the 7th. Okay, and that's as far as we can simplify. I can't combine u's and v's, so that's it. Second property, if I'm raising a power to a power, I multiply the powers together. So we really have two things inside the parentheses here, right? A 3 and a y. So if I don't see an exponent, both of those are being raised to the first power. So I need to then raise both of those to the negative 3rd power. So I'm distributing that power in. So I would get 1 times negative 3 is negative 3. So I'll have 3 to the negative 3rd power. Same thing with the y. I'll have y to the negative 3rd power. Now, in the directions, it says your answer should contain only positive exponents. Well, I've got negative exponents here. So to fix that, we can take negative exponents to the denominator. So I can take both of these things to the denominator and just write this as 1 over 3 to the positive 3rd times y to the positive 3rd. And I mean, you could go ahead and actually cube 3 and make that 27 if you want, but you don't have to either way. Okay, so 1 over 27 times y to the 3rd or 1 over 3 cubed times y to the 3rd would both be perfectly acceptable answers. Then the third property we talked about, which is in both 3 and 4 here, is the quotient property. If I'm dividing two things with the same base, I subtract the exponents. So if I just look at the numbers, again, if there isn't a coefficient, we know that coefficient is 1. So I've got 1 over 2. I cannot reduce that. We think about that as just a fraction to see if we can reduce it. Can't reduce 1 over 2, so that part will stay. Then I've got x to the negative 1st over x to the negative 2nd. If I subtract those exponents, negative 1 minus negative 2, that would be the same as negative 1 plus 2, which would be 1, right? So this would be x to the 1st power. Then, if we don't see anything here, right, we can think about that as 0, okay, or y to the 0 power. And so if I say 0 minus 2, I would get y to the negative 2nd. Or we could just think about this as, well, since there's no y here, this y to the 2nd will just stay in the denominator, right? So to clean this up a little bit, we can just say this is x over 2y squared. Similar idea over here. And 2 over 3 does not reduce, so that part will stay. Then I've got x to the 1st over x cubed. So if I do this subtraction, 1 minus 3 would be negative 2. So I would get x to the negative 2nd. And 2 minus 3 would be the negative 1st. Well, since both of those exponents are negative, I can take them to the denominator and write this as x squared times y to the 1st in the denominator. Another way to think about it is just, well, if I've got 1x on the top, 3 x's on the bottom, I would cancel out one pair of those x's, and I would be left with x times x in the denominator. Similar idea for the y's. Got 2 y's up here, 3 y's down here. 2 pairs would cancel, and I would just be left with 1 y in the denominator. Right. Any questions on properties of exponents?
I did all this.
All right, I will put your points in.
So
that's not true. So the next section then was just lazy 7, right? Rewriting logs as exponentials and vice versa. Rewriting exponentials as logs. So For 5, base of the log becomes the base of the exponential, and this is the exponent, equal to this. So we would say x to the negative 7th power equals y. Same idea on 6. Y to the 5th power equals x. Then, if I have an exponential and I want to rewrite it as a log, the base of the exponential becomes the base of the log. So this would be log base 4 of y equals x. Over here, base of the exponential becomes the base of the log. So log base a of 159 equals b. So hopefully these are easy points on the test. Right? We use these later on, right, to solve exponential and log equations. All right, so the next part on the front here was expanding and condensing logs. So first, we're given a condensed log and we want to expand it as far as possible. So first, if I'm dividing 2 logs, I can split that up into 2 separate logs by subtracting them. So I can say this is the same as log base 3 of a to the 4th minus log base 3 of b to the 6th. Then, if I have exponents, I can bring those out front as coefficients. So I could say this is 4 times log base 3 of a minus 6 times log base 3 of b. That's as far as we can expand. Then, the other property we talked about was if I'm multiplying things inside of a log, I can split that up into separate logs by adding them together. So here I'm multiplying 3 things together. I can have 3 separate logs. So I can make this log base 8 of x plus log base 8 of y plus log base 8 of z to the 4th. Then again, if I have an exponent, I can bring that out front as a coefficient. So that only applies to this last log. So these first 2 will stay the same. Log base 8 of x plus log base 8 of y. Now if I bring that exponent out front, 4 times log base 8 of z. 11 and 12 then, we're going backwards. We're given an expanded log, and we want to condense it as far as possible. So the first thing we can do is look at our coefficients and bring those up as exponents. So I can make this log base 6 of x to the 4th plus log base 6 of y squared. Now if I'm adding 2 logs together, I can combine them by multiplying what's on the inside. So I can make this log base 6 of x to the 4th times y to the 2nd. Okay? I've seen some people making this an addition sign on the inside. Make sure that you're not adding these 2 things together when we combine the logs. Right? If we're adding 2 logs together, that becomes multiplication on the inside. All right? Then the other one, I'm subtracting, I will end up dividing what's on the inside. So again, first thing, bring the exponents, or bring the coefficients up as exponents. So this will be log base 5 of x to the 4th minus log base 5 of y squared. Then divide what's on the inside. So log base 5 of x to the 4th over y squared. Any questions on anything on the front?
All your outputs.
That is actually different.
Oh, okay.
So that, yes, you cannot write it like that. Any other questions on anything on the front? Usually. Alright, on the back then, we are solving a bunch of equations. So the first 3 on the back we have a log equal to a log. Okay, whenever we have a log equal to a log, all we need to do is take whatever's on the inside of those logs and set that equal. So here, I already have one log equal to one log, so I'm just going to say 2n minus 5 equals 23. Solve this. So this is pretty straightforward to solve. Right? Add 5 to both sides, divide by 2, and we get m equals 14. Now remember, on these we do have to check our answer. Remember, we could do everything correctly and still get an answer that doesn't work when we plug it back in. Okay, so we do need to check that. So here, if I get my 14, plug it back in here for m, 2 times 14 is 28, minus 5 is 23. It works. Okay, and by works, remember, we're just making sure that we don't get a negative inside of any log. 23 is obviously a positive number, so it works. Okay. Same idea for 14 here. I already have one log equal to one log, so we can use this one-to-one property. So I'm just saying 3b plus 10 equals 4b plus 6, and we're solving. So I want to get my b's on one side. So keep b's positive, it probably makes sense to subtract the 3b over. Then subtract 6. And we get that b is equal to 4. Now, plug it back in and make sure it works. So if I plug 4 in here, 3 times 4 is 12, plus 10 is 22. 4 times 4 is 16, plus 6 is 22. It works. Same idea for 15. I've got one log equal to one log. So I'm just going to go ahead and set 2n minus 9 equal to 3n plus 5. Get the n's on one side, so I'll subtract 2n over. Get negative 9 equals n plus 5. Subtract 5, we get n is equal to negative 14. So, let's check it, plug it back in. If I plug negative 14 in here, 2 times negative 14 is negative 28. Negative 28 minus 9 gets me negative 37. That's no good. Right, we get a negative number inside the log. Okay, so I mean, we did all of this correctly. But what we found was an extraneous solution. Right? Negative 14 does not actually work. So for this problem, there are no solutions. We okay on those? Nice. Then on 16, we have a similar situation as the last three, but there's one extra thing we have to take into account. I've got two logs on the left side of the equation here. I need to combine these into a single log before I can take what's on the insides and set them equal. So if I'm subtracting two logs, I can combine these by dividing what's on the inside of the log. And so I can say this is the same as log base 9 of negative 5x divided by 2. And I'm just taking what's on the insides and dividing. I didn't do anything to this side. So now I've got one log equal to one log. Now I can set what's on the inside equal. So I can say negative 5x over 2 equals 41. Now to get x by itself, multiply both sides by 2. Since I'm dividing by 2, that would cancel out. We get negative 5x equals 82. Divide by negative 5. And we could just leave this as a fraction. I don't think that reduces. Or you could write it as a decimal. Either way. I think as a decimal, it's like negative 16.4. Okay, but you could also just leave it as negative 82 over 5. But then again, we need to check and make sure this works. So the only place I have an x in my original problem is right here. So I would take negative 16.4 and plug it in for x. Negative 5 times negative 16.4 gets me a positive 82. So that works. It's good. Remember, our answer can be negative. Okay, that is possible. Our answer can be negative as long as we don't get a negative value inside of the log when we plug it back in. All right. Any questions on those?
So, what was the difference between 15 and 16?
So, when we got negative 14 as our answer, and when I took that and plugged it back in here, inside of the logs, we have 2 times negative 14 minus 9. So 2 times negative 14 is negative 28. Negative 28 minus 9 gets me a negative 37. So when I took my answer and plugged it back in, we get a negative number inside of the log. Whenever we get a negative inside of the log, it's no good. We can't have that. But here, when I took my answer and plugged it back in, negative 5 times negative 16.4. Since they're both negative, that would actually end up being a positive number. Right? That would be positive 82. So I'd still get a positive number on the inside. That means this is a good answer. Any other questions?
So you should always put it back in.
Yeah. Always, when you get your answer, always plug it back in every place you see the variable in the original equation to make sure that you get a positive number inside of that log. Any other questions? All right, then 17 and 18 were our second type of log equation. So on these, we have a log equal to a number. Okay, we do not have a log equal to a log, so we have to solve these a little bit differently. I still need to combine the 2 logs that are on the same side of the equation. So if I'm subtracting, I can combine this into a single log by dividing what's on the inside. So I can say this is log base 9 of 3x over 8. And then that's still equal to 1. But since there is no log on this side, I can't take what's on the inside of the logs and set them equal. Whenever we have a log equal to a number, we have to rewrite this as an exponential, or a lazy 7. So from here, I would say 9 to the first power equals 3x over 8. 9 to the first power is just 9, right? So I would multiply both sides by 8 here, and get 72 equals 3x. Divide both sides by 3, and we get x is 24. Similar idea on number 18. I need to combine these 2 logs into a single log, log on the left side of the equation. So I'm multiplying what's on the inside here because I'm adding these 2 logs together. So log base 9 of 3 times x plus 8 equals 1. And so I can go ahead and distribute this 3 through here and make this log base 9 of 3x plus 24 equals 1. But again, I've got a log equal to a number now, not a log equal to a log. So whenever we have that, we need the lazy 7. So I would say 9 to the first power equals 3x plus 24. Okay. Subtract 24 over. Negative 15 equals 3x. Divide by 3. We get that x is negative 5. Any questions on solving log equations? All right, then the rest of the paper is solving exponential equations. So 19 through 22 are the first type that we looked at, where we can rewrite both sides of the equation with the same base in order to solve. And so on 19, I need to rewrite both sides with the same base, right? Hopefully we can recognize that 625 and 125 are both powers of 5. So I can rewrite 625 as 5 to the 4th power, And I don't expect you to just know that off the top of your head. You can use the calculator and do a little bit of guessing and checking. Okay, so this would be 5 to the 4th, 2 to the negative 3x power. And then 125 is the same as 5 to the 3rd power. Now if I've got a power to a power, I multiply those together. So this would be 5 to the negative 12x equals 5 to the 3rd. Once I have this, once I have the same base on both sides, I can just drop the bases and set the exponents equal. So negative 12x equals 3. Divide both sides by negative 12. And this fraction, 3 over negative 12, would reduce to negative 1/4. Or if you want to write it as a decimal, negative 0.25. Either way is perfectly fine. All right. 20, same idea. I'm going to rewrite both sides with the same base. So 27, I can rewrite with a base of 3. That would be the same as 3 to the 3rd power. And that's raised to the a. Then 1 over 3. Okay, we talked about we can rewrite 1/3 negative exponent. Right? 1/3 is the same as 3 to the negative 1st power. And then that's raised to the 3a plus 3. So again, I'm multiplying the exponents here if I'm raising a power to a power. So this would be 3 to the 3a. Then here, I would need to distribute this negative 1 to both of these pieces of my exponent. So this would end up being negative 3a minus 3. Now that I have the same base, I can set the exponents equal. So 3a equals negative 3a minus 3. So I can add 3a over to here. We get 6a equals negative 3. Divide by 6. And negative 3 over 6 would reduce to negative 1/2. You okay with that one? Similar idea for 21. You want to rewrite both sides with the same base. There are actually a couple of different ways that we could do this. We could rewrite both sides with a base of 2 or 4. Either way, we would end up with the correct answer. Rewriting with a base of 4 is probably the one that more of you did. So I will do that. 64 is the same as 4 to the 3rd power. That would still be raised to the 3 minus r. 16 is the same as 4 to the 2nd power, and that would still be raised to the negative r minus 3. So I need to distribute my exponents on both sides here. So 3 times 3 is 9. 3 times negative r is negative 3r. Then I need to distribute the 2 over here. So this would be negative 2r. 2 times negative r would be negative 2r minus 6. Now I can just take the exponents and set them equal. So I'm going to run out of room. I'm going to come over here and do that. So 9 minus 3r equals negative 2r minus 6. Now I want to get the variables on one side. So it doesn't really matter which way we go. We could add 2r over to here or add 3r over to here. I'll add 3r over to this side. So negative 2r plus 3r is just r. Then I can add the 6 to the other side and get that r is equal to 15. And then 22 ended up being the easiest one of all of these because I don't even need to rewrite both sides. Right? They already both have a base of 5. So I can just go ahead and set the exponents equal here. Say p plus 1 equals 2p minus 1. Get the variables on one side. So minus p, then the numbers on the other. So we end up with p equals 2. Any questions on exponentials of this type? All right, then the final section was solving exponentials where we could not get a common base. Okay, this one we had to use logs to solve. So on all of these, the first thing that we want to do is isolate the exponential. Okay, that means get it by itself on one side of the equation. So in number 23, my exponential is this term, 14 to the k minus 4. So I want to get that by itself. So to do that, I want to subtract this 10 over. So we'll get 14 to the k minus 4 equals 13. Now, once I have the exponential by itself, I want to lazy 7, rewrite this as a log. So the base of the exponential becomes the base of the log. So I will have log base 14 of 13 equals k minus 4. Now this we can put into the calculator. Right, is everybody comfortable putting a log into the calculator? Does anybody want me to show you how to do it up here? Alright, it's math. Scroll all the way down to log base. So if we put this in the calculator, what do we get? 14 of 13. Points 9719. So then I've got one more step. I would add 4 to both sides, and we would just end up with 4.9719 is equal to k. Right, so it's a similar process for the rest of these. Okay? Here, get the exponential by itself, so subtract 2, get 16 to the negative 9x equals 96. Now rewrite it as a log. So log base 16 of 96 equals negative 9x. So log base 16 of 96 is 1.6462. Then to get x by itself, divide both sides by negative 9. We get negative 0.1829. And remember, we're rounding to 4 decimal places on these. Okay, it says in the directions, it's round to the nearest 10,000. That's 4 decimal places. So on 25 then, I need to get rid of this 9. So it's being multiplied. In this case, I would need to divide that 9 over. So we get 8 to the negative 8p equals, divided by 9, 8.88 repeating. More. So once we have the exponential isolated, rewrite it as a log. So lazy 7, I will end up with log base 8 of 80 over 9 equals negative 8p. So if we put log base 8 of 80 over 9 into the calculator, we get 1.0507. Then just divide both sides by negative 8. And we end up with negative 0.1313. And our final problem on the review here is pretty similar. We need to isolate the exponential. So add 5 to both sides. Get 9 to the x minus 7 equals 46. Now rewrite it as a log. So log base 9 of 46 equals x minus 7. Put log base 9 of 46 into the calculator. And we get 1.7425. then I would just need to add 7 over, and we would get 8.7425 for our final answer. Did you round wrong? 8.7424. Yeah, so it's 8.74248. So since the number after this is larger than 5, we would round this 4 up to a 5.
So you want this around to the
I'm done. So I'm
We
rounding.
can round it up there before the 7.
You're right. So I guess I should have left this as after go out to a few more decimal places. But then, since this number is larger than 4, right, we would round this up to a 5. We actually round.
I can do that.
All right, so that's the review. Any questions? The test tomorrow will have 20 questions, so it will be a little bit shorter than the review. All right, 20 questions.